So we are going to move on with the continuation of the question and answer section with the two of the summer school, section 1 and 2. Mark the pending question. We have question number 15, which says that how can you identify the model to use for a particular application? What is the process involved in data modeling if you want to develop your own algorithm or your own model, as the case may be? Well, identify a particular, let me clarify a couple of points. Let me start by clarifying for us. Usually people do confuse model with algorithm. You see, there are two different things. You see, when you have algorithm, which is machine learning algorithm, ML, for example, k-nearest neighbor, when you carefully select it and you add your data to it, provided with the appropriate data, this is when, and then the modeling takes place. This is when you are going to produce model. So that is the outcome of carefully selected and optimized machine learning algorithm plus the appropriate data set will result in what we call model. So sometimes people use it interchangeably. It is not correct. So we don't talk of model until when we have worked with our data using the appropriate algorithm. Now, so in this case, maybe you want to say what we can reframe the question that how can we identify the algorithm to be used for a particular application? You see, it's not something that you can be definite about. There is usually what we can refer to as maybe a kind of a trial and error is involved. You have to check which algorithm is going to work for you. If you remember in one of our previous lectures, we did mention that there's no free lunch principle. So that is, there's no algorithm that is inherently better than others. So we have to try and see. And based on my own personal experience, I usually say, let the data speak. Let the data speak. So no one can categorically tell you this is the algorithm that's going to work for this data. You have to try and check it out, because sometimes data set coming in might even make some of the algorithm that we have been using successfully in several applications might not be able to work for a particular problem. So this is a possibility. So which means saying that, okay, this is the best algorithm might not really come in as the case may be. So we have to try. And the rule of thumb is to start with simple algorithms. First of all, start with simple one. See, try simple one first, like k-nearest neighbor, like decision tree. Then you keep increasing the complexity as the number of data sets increases. If the number of data sets is not much, very few data samples, then you go for very simple algorithm. Maybe they can be able to do that, like k-nearest neighbor. One unique sophisticated algorithm that often break this rule is what we call support vector machine. Support vector machine. Support vector machine has been deputed with the capability of working on very few data samples. It's a little bit it's away from the standard known system that once the data set is increasing, then you can go for more sophisticated algorithm than neural network, support vector machine. However, support vector machine has demonstrated its own capability to work even in the face of few data samples, just like simple algorithm, even though we cannot regard support vector machine as simple algorithms because it is based on sophisticated mathematical statistical background. However, it has that unique capability that it can work when your data set is very few. We've demonstrated in several applications. However, that doesn't mean that support vector machine is going to work for you in all situations. In fact, by the way, if someone says the best algorithm is A or B or C, no, that is not the correct way to say it in machine learning. There's no algorithm that is best for a particular problem. We have to try and see. The fact that it works for one problem does not guarantee that it's going to work for another problem. So we have to try the algorithm while always bearing in mind what we call let the data speak. So the data set will go a long way in determining if the algorithm is going to work or it's not going to work. So that is why we advise us when you have a new data set, start with simple algorithm like k-nearest neighbor, decision tree, and host of other simple algorithms. And then if the data set is much, then you can try other algorithms like neural networks, perfect machine, and a host of others. So that is on the first part of the question. And what is the process that is involved in data modeling? So if you want to develop your own model, I believe you've tried to talk about your own model here. Like I see people do intervene, that can interchange model for algorithm. Now, you want to develop your own model. We mentioned earlier, there's what we call the machine learning modeling procedure or paradigms. So which is an iterative process. That is, it's not something you do at once. You see, it's very rare you just run data through an algorithm and everything is fine at once. Very, very rare, almost near impossibility. So there's going to be a kind of looping or iteration. Let's look at this generalized framework. It works for any machine learning paradigm you want to use. Do you want to use supervised learning, unsupervised learning, and a host of others? It works fine. Now look at it, you have your data preparation stage, when you get your data ready. So you have the feature engineering. So getting your feature in the appropriate way, feature selection, and also for that is involved. We can refer to some of our earlier videos. We have described each of these procedures, one after the other. Then here is where you select your algorithms. And like I said, start with very simple ones and see, you do data modeling here. So put in your data, you have prepared your data in the proper format. If you want to use Weka, you put in Excel or in the ARTF format. The features are already selected appropriately, and then you go to modeling. So once you do the modeling, then you have to carry out what we call performance measure analysis or model evaluation. We call model evaluation. So you need to check your model. What is the generalization ability of your model? Is it performing well on the testing set, most importantly? So once you check the results, maybe at a go, I'm very lucky, I got like 75% accuracy for my testing set. This is interesting for a start, but I will not stop that because maybe I can still achieve 100%. Who knows? That's why you have an iterative process. And the iterative process can take you back to the data modeling stage, just a step backward, in which case, maybe you need to optimize the algorithm. Maybe I'm using k-nearest neighbor. We have described this extensively. You can check out our videos. So I have k-nearest neighbor. I want to change the number of k. Presently, I'm using k is equal to 1. That is the number of neighbor I'm using to do my classification is k, or regression as the case may be. I want to increase it to 3, to 5, to 7. This is called a simple optimization of the parameter. The hyperparameter, we need to optimize the hyperparameter, and the hyperparameter for k-nearest neighbor include the k value, that is the value of number of neighbors I'm going to use, and also the distance measure that we want to use. What is the distance measure that we want to use? Like Euclidean distance, the Manhattan distance, and a host of other distance measure. We have to select them through the simple optimization procedure we described. So going back might just mean that, okay, I need to optimize my parameter. Instead of 1, let me change it to 3. When I change it to 3, the accuracy moved to like 85. That is interesting, 85% accuracy. This is good, that's improvement. I shouldn't stop there. I went to 5, it moved to 95. That is interesting. I keep changing it until I cannot get anything. Maybe I move to 7, and suddenly it dropped back to 86. It means that maybe 5 is the optimal hyperparameter for that particular problem I'm solving. So this is why the iteration might just involve you to go back and do optimization. But sometimes you might try k-nearest neighbor, it might not work. You try all the optimization of the parameter, the best you are getting is maybe just 72% or even lesser. maybe you might need to change the algorithm. You see, you might need to try another one, decision tree, optimize it again and see if it's going to work for you. So this is the first iteration step. You might need to go back to the next previous step. Sometimes changing all the algorithm might not work for you. You have tried all the possible algorithm, you are not getting something good. Maybe you might need to go back. You might need to go back to the feature engineering. Maybe you have selected the wrong features. Maybe the features have been wrongly combined together. You might have to go back here. And sometimes things might be so worst that we might have to go back to the beginning again, start all over. Data preprocessing, data preparation. Maybe wrong data have been given to you by the client that gave you that project. You might have to go back to the client. Hey, the data is not good. We need to start again. We might need to do some missing value treatment. We might need to do some outlier, whatever we might think of. There's another video where we describe data preparation or data preprocessing. But this is just telling us the generalized machine learning modeling, that it involves a lot of iterative procedures. It could be just the previous one step backward, or going back to feature engineering, or even going back to the beginning, data preparation, getting your data afresh from the client, replacing the data, or try to reprocess the one that has been given to you, doing better missing value treatment, doing better outlier detection and model and treatment, and also for other stuff that we've described under data preprocessing. Now, this is the generalized, generic framework to be used. And sometimes, if this supervised machine learning, in this case, we can make it, listen, another flow chart to tell us what to do. You have the data gathering and preparation. So where we call everything a data preparation stage. So you gather your data, you pre-process it. It may be the missing value you are treating. It could be the outlier you are trying to identify, and also further preparation you might do. Then the model building here, you are going to divide your data into 2 or 3, as the case may be. You're going to have the training set, and then the testing set is going to be kept separate to be used for checking the performance of your model that you are building. So in the model building procedure, you build the model, then you use the testing set to check. Because is it working fine? On unseen data, you bring the testing set here to check. Here we're using the training set for building the model. We're using the testing set or validation set to check it out. Is it doing fine? If it's doing fine, then we continue, we finalize our modeling. But sometimes need to refine the model. Yes, we need to refine it. It's not doing fine. We're only getting 75% accuracy. So we go back. We do hyperparameter optimization. We go back again. We keep going back until our checking is saying, no, everything is fine. We are all right. We've gotten the maximum possible. Then we move forward. We move forward. We build the final model using the hyperparameter obtained. And then you validate the model. If you have another data set, that's why it's always good to divide your data into 3 parts. If the data is sizable, we have the training, then we have the validation, and we have the testing set. You see, you use one here for building, another one to check if it is fine. Then if everything is fine, then you build the final model and then you validate. Sometimes we can bring new data from the client, to do the final validation of our model to be sure it is working fine. Then prediction using the model, result analysis and interpretation of what you have gotten, identification of hotspot and future work that you want to do. This could be another generic framework that you can use to actually develop your own modeling. So either you follow this is a generic one for all paradigms, why this one for maybe the training system, the supervised machine learning framework. Having done this, these are the procedures that you have to take to get your model built. And we've explained this in detail in some of our previous videos. We refer also to actually check it out later on. Now, next, we move forward to the next question is question 16. Does machine learning generate error matrix to check accuracy? Yeah, well, depending on the problem we're solving, the system will generate for us the outcome, the output. One of the very popular performance measures that we do use in classification problem is what we call the confusion matrix. You see, the confusion matrix will be like this. You have the correct, you tell us how many are correctly classified. These are the first, this is maybe this is positive, this is negative. The original one is positive, this is negative. How many are, what is the first positive, what is the first negative? This is 5, and then this is 4, and then this is 25. These are the correct classification. As the case may be, these are the correct classification. That is, this is positive class predicted as positive. This is negative class predicted as negative. Then in this left diagonal, you have the wrong classification outcome. That is, this is supposed to be positive, but it has been predicted as negative. We call it false negative. False negative. This one is supposed to be predicted as negative, but it has been predicted to be positive. We call it false positive. And sometimes we need to do detailed analysis of the implication of such. Because for medical problem, false negative is a serious problem. It's a serious mistake. Of course, we don't want any mistake, but some mistakes are a little bit acceptable or manageable. But false negative for medical prediction is very dangerous because you'll be predicting that somebody is not sick. Meanwhile, he's sick. So you go home and then you could develop complication and the like. So we don't want our machine learning model for health prediction to have false negative mistakes. So sometimes we have this kind of matrix. We call it confusion matrix. It to spell out what is the correct prediction or what are the mistaken prediction. Then we can take a decision. For example, we have a model that is generating 0 false negative, but the mistakes are coming from, the mistakes are all 8. You see, compared to another one that is generating 7 mistakes and 1 mistake for the false negative. I better go for this one because the mistakes are coming from the less challenging side. That is for medical application. If you go to another area, it's going to be a totally different interpretation. Now, so we have something like that, yes, you have error matrices to check the accuracy of your work. And now say, even when you are doing regression problem, when you are solving regression problem, yeah, you have an output that will tell us directly, since in the regression, you are predicting the actual value. Yeah, you have your output that's going to tell us this is the actual value given, this is the predicted value. Maybe the answer was 32.5, and our system predicted it to be 33.5. So you have another one, the answer was 45.6, and then the prediction actually is like around 45.7. So we can actually try to find the difference between the predicted and the original and the predicted value. So this kind of matrix is often generated. Then we can take it out to see actually how is our predictive model doing. And sometimes you might actually plot it. You can plot the actual prediction and also plot the actual value given. This is the given value originally, and the one predicted by your model. You can plot them on the same plot, and then you can see how close they are together. This is very important when you are describing the outcome of your regression problems. You need to let us know how close are they. Maybe this is very close together. You can use one is dot and the actual is dot and the other one is star. So we how many star and dot are on top of them, of each other. Sometimes we are able to have very close prediction that almost the point are staying on top of the actual value given, but sometimes also you have differences. This is in addition to other quality measure that you can actually check out. So that is how the matrices can actually show to us the accuracy of our model. Then we said, now another question is, which degree program does one need to study to specialize in this area, please? Okay, another very interesting question. Well, as these days, specialization is become very fluid. I mean, that is the partitioning between specialization is actually disappearing gradually. Of course, because even artificial intelligence itself came from different background. It combined different ideas from psychology, philosophy, I mean, biology, then to algorithm mathematics, and host of different fields came together to actually form it. The same thing goes for machine learning. So indeed, to be a the scientist or data analyst, anybody can become data analyst. You just need to go and get some training in this area and you get it done. Of course, if you really want to be a specialist in this area, then computer science, information system, or anything related to those areas, those are for young ones who are aspiring to select their majors. Then they can go into computer science, information system, artificial intelligence, and host of things that are related to computer science. So they can be able to build the algorithm on themselves. They'll be able to do programming as it should be. However, for someone who is already on the field, you already have your own degree. Actually, practically any degree you have presently, you just need to train yourself to become data scientists. And like I said, things are changing now. You see, a lot of people from different backgrounds, they are doing great work in the field of data science. I've had students from physics today is doing a great job using machine learning in his own field of specialization. So anyone who's interested can actually get him or herself trained to become data scientists. You don't need to go and study computer science afresh before you can become data analyst. So this is a simple way to just get this particular question answered. But for the youth who are just about to start their career, yes, any computer-related field could be good for them if they want to really specialize in this area. Yeah, but for those who are already on the field, you don't need to go back and study computer before you can become data scientists. You can always log in, search for the appropriate program, and then you can get yourself trained on how to become a data scientist or machine learning engineer. So, okay, can you give the link for the certificate? Okay, for the certificate, the coordinator team for the summer school, they are working on that, and very soon, in a couple of days, hopefully, so those certificates will be given out to the participants, inshallah. Then the next question is question 19, impact of machine learning on depression. Impact of machine learning on depression. I want to believe maybe this questioner is asking of, can we use machine learning to solve depression problem or to detect depression or also other stuffs? Well, like we explained earlier, and we've had several editions of our Saturday lecture dedicated to different applications of machine learning. One of the areas we actually delved into is how we can use machine learning to analyze social media data. And it is getting very clear that one of the areas to quickly detect if somebody is having psychological problem, mental problem, or depression signs is through social media analytics. So we try to analyze the social media account of individuals, try to see what are the signs that someone is getting depressed. Before the problem actually come full blown, we can actually detect it earlier by looking to the social media through sentiment analysis and host of others. We've had students in the past who trying to say, okay, can we detect if somebody is having a mental problem through social media? Because these are issues that sometimes is very difficult or challenging to confront someone that, oh, we want to diagnose you, we want to check you. But by looking directly or indirectly into their social media through what we call sentiment analysis, we call it sentiment analysis. Sentiment analysis. So we try to analyze people on social media to see, okay, because when you are chatting with your friends, you are likely to be to be yourself, to be truthful. I mean, to be able to, you are likely to display your actual characteristics because you are free. You are not chatting with your authority. So you feel free. By so doing, data gotten from that can really represent your specific state of mind, which can indicate your mental health, your status as far as depression is concerned. Is he having any sense of depression? Also, there is no sign of his depression. We also discussed earlier, one of our people where they trying to analyze if somebody is having anxiety or non-anxiety as a result of COVID-19 pandemic. So in the same way, I believe depression is not left out of areas that sentiment analysis can actually help us to solve this kind of problem earlier before it goes out of hand.